Okay, that will be up in a minute, I hope. Yeah. While that's coming up, let me go over just a couple of things. I think I mentioned this before. Let me go over it now. I did pay attention when I put attendance in last Monday, but if any of you have not completed payment, please try to get that done. They never tell us when they're going to do it, but at some point they say, "Oh, unpaid students are removed from the roll." Okay, so we don't want that to happen. So, and if it does happen, you can usually talk your way back in, but it's a lot of hassle on you. So if you haven't completed payment, please get that done. If it's something that's in the works, let the business office know what those works are and that it will be coming up. Let them get an idea, and that way they may put a flag on you and not remove you from the roll or whatever. Okay, that's one thing. The next thing is, I'm pretty sure I mentioned this last time. If any of you were planning to come by for my office hours tomorrow, don't. Okay, I've got eye surgery tomorrow. That's why I had to go down and put a drop in my eye. Got to do it 4 times a day before the surgery tomorrow. And we have to be there at 5:30 in the morning, so I will not be on campus at all tomorrow. I thought maybe if they scheduled me for the afternoon, but I didn't think they were going to do that. No, they scheduled me for 5:30 tomorrow morning, so I won't be here. After surgery, they don't want you doing much of anything for a while. My wife thinks it's a few days. I think it's just that day, but whatever, they'll tell me tomorrow. But anyway, that will be done. I won't be on campus at all, period. Either campus tomorrow, so don't come by. After this, I've got a follow-up visit next Tuesday, and then I've got one other different appointment on a Tuesday later this month. But as far as I know, knock on wood, that's all for the term that I know that I'll be out. Okay. Any questions on anything before we get started? Okay. Your first test is being copied sometime, and so before you leave today, pick up the test. All right. I had planned to get it in yesterday, and yesterday fell apart like crazy. Okay. Now, for some reason, this took us to example 4. And I know we've done example 4 and 5. Why is it taking us so far? But yeah, this I think is where we pick up today. Is everybody? Yeah, okay. The theorem of Pappus, and if you got a text, this is on page 501. All right. Any questions before we get going? Okay. Theorem of Pappus, by the way, I don't even know who Pappus is. Pappus of Alexandria, this is about 300 AD. Greek mathematician, wrote 8-volume mathematical collection, is a record of much of the classical Greek mathematics. He didn't come up with all of it, but this seems to be one that is attributed to him. Okay, if you have a region R in a plane, and L is a line in that same plane, such that L does not intersect the interior of R at all, okay? So, R is some region. Now, usually capital R indicates rectangular region. Our example here is going to be a rectangular region. It doesn't say it has to be rectangular, just some region in a plane. Let L be a line in the same plane so it doesn't intersect any of the interior of R. It could touch the exterior but not intersect. If little r, now capital R is a region, little r is the distance between the centroid of R, this region here, and the line, wherever that is, okay, then the volume of the solid of revolution formed by revolving that region R about the line L is, surprise, surprise, the circumference of that would be 2 pi r, okay, yeah, 2 pi r times the area of that region. A is the area of r, whatever that region was. Notice 2 pi r is the distance traveled by the centroid, and remember, r is the distance from the centroid of r in the line, okay? Traveled by the centroid as it revolves around the line. In other words, the circumference of that circular path, okay? And this would give you the volume, and indeed it does. It's a lot like our shell method that we did before, okay? It's just, this is the actual physical part. Now, there are features of this illustration I don't really care for too much. It's pretty obvious, or a little bit obvious, that this is your region R in black. Why they have the purple plane here, I guess it's just to show you it's in the same plane, the region R is in the same plane as L, okay? Other than that, it's confusing, because you almost think it's this. No, it's not. It's just this region R here revolved around, and here's the centroid of R, okay, revolved around. Now, when they use the term centroid, that means you've got a laminar plane. You don't have any distribution of density or anything else. So this is, if this is a rectangular, that is the diagonal bisecting point right there. That is the center of that rectangle. Half this, half that, okay? And that's rotated around the line that's in that same plane as this, and that is your distance from the line to the centroid, okay? That's rotated around, and the side, the solid that cuts out, this would be a right circular big fat washer, okay, or something like that. That would be the volume that you have. Again, it's just the same principle of the revolving of the area around the of our shell method. So I think, okay, theorem of Pappus can be used to find the volume of a torus, that's not the car, as shown in the next example. A torus is a donut-shaped feature, I like that a lot better, so donut-shaped solid formed by revolving a circular region around the line that lies in the same plane as that circle, but does not intersect the circle, okay? So here we have it. Find the volume of the torus, the donut, shown in this figure here, which is formed by revolving the circular region, x minus 2 squared plus y squared equal 1. Now what does that tell you about the circle? This equation right here, what does that tell you about the circle? Anything? Radius of 1, right there, that's r squared, 1 squared is 1, okay? Second?
You moved it over to.
Okay, yeah, okay. So its center is at 2, 0, okay? The center of the circle is at 2, 0, right there. That's where this 2, and since you don't have anything up to that, that's a 0. So you're revolving, okay, by the volume of the torus shown here, formed by revolving circular region bounded by this, about the y-axis. Y-axis doesn't intersect the circle, so you're okay. It's shown here because the radius was 1, you're 2 away, so you're all right there, revolved from going around the circle. Obviously, the scale's a little different. That looks a lot bigger than that circle there. I wish they'd have done, maybe it's optical illusion, but it seems a lot bigger to me, okay, by going around the y-axis. So how would you do this? How would you find that volume? start it off. Whoa, let me start it off in the right color. V is equal to blank. That's where you, no, okay. What? 2 pi r. What is your r there?
2.
Second?
2.
Ah, yes, this r is 2. 2 pi times 2 times area of the circle. Very good. What is the area of the circle? Of radius 1. What's the area of the pi r squared, and r is 1? It's just pi. Okay? So that would be times pi. Okay? I guess I should have written out the volume is 2 pi r times the area of that circle. And this area was pi r squared, which is pi times 1 squared, which is pi. Okay. So, what do we have? 2 pi squared, or 4 pi squared, or however you want to say it, 4 pi squared. That's the volume of that torus. I hope. Let's see what they get. From the figure, you can see that the centroid of the circular region is at the center of the circle at 2, 0. So the distance between the centroid and the axis of revolution was r is equal to 2. Because the area of a circular region is pi, because the radius was 1, pi r squared, that would just be pi. Volume of the torus would be 2 pi r times pi, which is 2 pi times 2 pi, which is 4 pi squared. And they may even give us approximately what that is. Pi squared is awfully close to 10, 3.14 squared, pretty close to 10, and that, of course, is 4, so that's pretty close to 40. That's close enough for government work. About 30.5 square whatever unit, cubic whatever units you have. Does that make sense? All right. Now, homework exercises here. I think I've given most of these before. Do either 5 or 7 or both. They're both a Calc Chat. 7's a Calc View. Do 9. It's a Calc Chat. 11 or 13. Both are a Calc Chat. 11's a Calc View. 15 to 27. They're all a Calc Chat. 15's a Calc View. 29's a Calc Chat. 31 or 33 or both. They're both a Calc Chat. 33's a Calc View. 35. It's dropping my eye is not helping my vision any. 37 or 39. They're both a Calc Chat. 37's a Calc View. You can look into doing 41 and or 43. They both should be, or at least some hints at Calc Chat. Any of the odds 45 to 49, they should all be at Calc Chat. 51 should be at Calc Chat, and 53 at Calc Chat. And as if that wasn't enough for you, there's a second theorem of Pappus that they give you here. Why don't they not put it in the text of the book? I don't know, but you can do 55 from that. And then 57 is another finding the centroid problem. Both of those are at Calc Chat. Any questions? All right. That finishes 7.6. Let's move on to 7.7. Fairly long chapter. This is the last section, and we also did, no, I guess we just started with chapter 7. That's why I was having trouble finding the test for it. Don't know why. Okay, we'll go from the current slide here. Okay. Section 7.7, continuing in Chapter 7, which is applications of integration. The last application will be talking about fluid pressures and fluid forces. okay? 7.7. We'll find fluid forces, pressure and fluid force. That sounds like a good objective for that section. Now, what in the world are we talking about here? Pressure is defined, this is good physics definition, the force per unit area over the surface of a body. Okay, force per unit area. Now, if you have trouble remembering that particular formula, I bet you some of you have put air in your tires before, right? And what was your goal from that? What were you looking for in your pressure? So many PSI. What in the world does PSI stand for?
Pounds per square inch.
Pounds per square inch. Pounds is a force, area is a square inch. So if you just remember the unit per pressure, pounds per square inch, that should tell you what your definition is, force per unit area. Because pound is a measure of force, and square inch is a measure of area. That's the only reason that's helpful to remember what pressure is. In general, pressure is proportional to the depth of an object in the fluid. Okay? So, definition of and by the way, when they say fluid here, a fluid is either a liquid or a gas. Fluids are not just liquid. Sometimes we think of that. A fluid may be a gas. We're under the influence right now of the fluid, the gas of our atmosphere. Okay? Anyone know how much pressure we're under? Oh, good deal. Good guess. 1 atmosphere of pressure. All right, which is also in PSI. No, 14.7. Almost 15 pounds per square inch. Now, if you think a square inch is about like your 2 thumb joints there, that's about a square inch. Just think how many square inches cover your body. Multiply that by 15, that's how many pounds of atmosphere are pushing on you right now. That's a lot. Why are we not crushed? Because our bodies are pushing out with a little bit more than that. That's why when we do have a cut, the blood comes out, not sucking air in. Okay? So we have at least that much pressure pushing out on us. Okay? Now, it also leads to why I think one of the most dangerous jobs ever undertaken. You all remember when we had a space station, meaning we, the U.S., but basically it didn't maintain its orbit and it crashed somewhere in the Indian Ocean or near Australia or somewhere over there. And then we had to share with the Soviets for a while, and Soyuz was the name of their space station. And they didn't have a shuttle fleet like we did, so they had unmanned cargo ships. They fired up there, and then they controlled them and brought them in and banked them up the thing and replenished that. And occasionally they'd have people in them too, and they would do that, but usually unmanned. And one of those didn't have a very good melding of the two one time. It crashed into the space station and damaged much of it, and the people inside basically had to get into a tiny little compartment in the center and hope that someone was going to come and rescue them. And they stayed there for weeks in an incredibly confined space. I think they were all cosmonauts. I don't think we had anyone up there at the time. And they didn't have a shuttle fleet to do what needed, so we sent our shuttles up and did repair on that space station outside. Okay? And if you think about that, a cargo ship crashing in, there had to be a lot of jagged metal, right? You would think if things had been damaged like that. And that's what they were out there repairing. Of course, they were wearing big, bulky spacesuits. Why were they wearing big, bulky spacesuits? Okay, because out there's no pressure. There's no atmospheric pressure to speak of, and they needed pretty close to 15 psi. Probably they could do it a little less. Pounds per square inch over their whole body, so that's why they were big pressure. So they were big, awkward, and they also, the other reason, silvered, so it would reflect most of that harmful radiation. It gets blocked by our great atmosphere that is above us, because otherwise they'd be toast in very few minutes. Well, not instantly, instant toast. Their death would be long and prolonged and painful, because the radiation would be quite deadly, but not immediate. Okay, probably, I don't know. But they had to have these big, bulky spacesuits. So they were out there in these big, bulky spacesuits trying to repair jagged, metal. If one piece of jagged metal had ripped their spacesuit, which would not have been an easy thing to do, but still doable, all that pressure would be gone. Which means also all the gases in their body and probably most of the fluid in their body into outer space like that. The radiation wouldn't have a chance to kill them. They'd be dead long before that, because they have about 15 pounds per square inch pressure inside their body, nothing on the outside. There they've been spewed into space. Now, I may have over-dramatized that a little bit, my prerogative, but that had to be one of the most dangerous jobs ever attempted and accomplished quite nicely. They got it running again. I don't remember how many deployments it took, but they did get it running again. So, pressure is proportional to the depth of the object in the fluid. We're 1 atmosphere deep and below our atmosphere. They were out there outside of the atmosphere, or most of it anyway. So, here's the definition of fluid pressure, and that's why I say it's not just liquids, but it's also gas. The pressure P on an object at a depth h in a liquid, they say liquid, in the fluid, is P is equal to WH. Now, what in the world is a W? W is the weight density of the liquid per unit volume. Okay? Weight density of liquid per unit volume, that would be pounds per cubic foot. Newtons per cubic meter. Okay? That would be your weight density. Okay? Weight per unit volume times how deep you are. Okay? We'll do how at depth h in the liquid, that would be your depth, that would be in feet or meters or whatever, and pounds per cubic foot times feet, that would be pounds per square foot, force per unit area. Newtons per cubic meter times so many meters deep, 1 meter we cancel out, newtons per square meter, force per unit area. So there's your pressure formula. Now, what I described with the atmosphere, that's a variable weight density, okay? Because different. If you're up there, ask those, how many people, record number of people died trying to scale Mount Everest this year. The density is much less up there than it is down here. That's why so many died. And also, one of the Sherpas broke his own record for number of trips to the peak. I think he's in the 40s now, and he's only in his 40s in age too, but that's pretty old, but he says he's going to keep going, so it's amazing. Okay, we're going to be dealing with things, possibly the weight density won't be varying that much. Okay, so here are some common weight densities of fluids in pounds per cubic foot. Ethyl alcohol, fairly light. Gasoline, lighter than that. Glycerin, much heavier than that. And this, again, is pounds per cubic foot. Kerosene, denser than ethyl alcohol and gasoline, but not nearly as good. Mercury, look at mercury there, folks. 849 pounds per cubic foot of mercury. Seawater, 64. Normal water, not seawater, fresh water, 62.4 pounds per cubic foot. Okay? And just to give you an idea, if you had a lead ball, pretty dense, right? Put it in a pool of mercury, it floats. Mercury is denser than lead. Lead floats in mercury. Don't be jumping in the mercury, okay? It's carcinogenic, okay? Not that you would sink or anything. When calculating fluid pressure, you can use an important physical law called Pascal's principle, named after Blaise Pascal, a French mathematician, but also quite a physicist himself. In fact, in a little bit, we're going to, I guess the book will get there, but if not, I'll tell you now. What did I say the unit in the SI unit was for pressure? What's the force unit in SI units? Newton per meter squared. Guess what a Newton per meter squared is named? It has its own name. A what? A Pascal. You're absolutely right. Named after Blaise Pascal. Now, we already use P for something else, so it's PA. And if you'll notice on your tire walls, when you're filling the tire with pressure, they used to say so many PSI, and then they started saying PSI, and in parentheses put KPA, thousands of pascals. Now they say KPA and occasionally put PSI. Tires are getting more metric all the time. Okay, we're not. Okay. French mathematician, and by the way, another potential paper topic. How did you go about finding it? You know, what's it used for? Lots of potential paper topics. Pascal's principle states that the pressure exerted by a fluid at a depth h is transmitted equally in all directions. All right, what do you mean by that? For example, in this figure, 765 here, the pressure at the indicated depth is the same for all three objects. As long as you're at the same depth, h, then the pressure is the same. It can be a slanted object, doesn't matter, flat object, vertical object. At that depth, all at the same depth, the pressure is exactly equal. At the same depth. Okay? So, Pascal's principle. Because fluid pressure is given in terms of force per unit area, I thought we were going to get there. Force per unit area. The fluid force on a submerged horizontal surface, if it's a horizontal surface, yay, we like that, because if you know the area, horizontal, it's all at the same depth, okay? They flipped the equation around and made it F is equal to P times A, which is very legitimate here. Then the fluid force on that is whatever the pressure is at that depth, at whatever depth you are, times the area. That's the pressure. No calculus involved. Just multiply. Okay? Now, here's example 1. Should be pretty easy, right? Find the fluid force on a rectangular metal sheet measuring 3 feet by 4 feet. 4 feet here, 3 feet there. That is submerged 6 feet in 6 feet of water, as shown in this figure. So it's all at the same depth, and that depth is 6 feet. So what would that be? The fluid force. Let me get my pen set up. I thought I had it set up, but that was on the last section. F is equal to, ugly. Okay. Is equal to, what was that formula? P times A. Remember that? Pounds per unit area times area. That would give you pounds. And we are measuring in that. So we need the pressure. We can calculate the area. What's our area? 12 what? Square feet. Force per unit area. So multiply by that. Now, how do we get the pressure? Is the weight density times the depth. Weight density for, wasn't it, water? 62.4. This is in pounds per cubic feet. foot. Okay, so this would be 62.4 pounds per cubic foot times the depth, 6 feet, times your 12 square feet. And notice, feet times square feet is cubic feet. They cancel out, leaving you pounds. So what is your fluid force on that piece of metal? I'll have to ask someone with a calculator to do that one for me. I'm not going to do that in my head. 4,400, you said? 92.8?
Yes, sir.
Okay. I think that's probably a few more significant digits than we have here. I would say that's around 4,000 pounds. Okay. I'm sure they're going to carry more digits than that, but I can't say for sure that I would agree they can. 4,492.8 pounds. Okay. And they mention here, well, they'll probably say it later. Now, I was going to say a little more about Pascal, but I'm afraid I might be a little off on this. My memory is, and I may be wrong on this, that he, I think, there were a few of them that ran together, it seemed like. Pascal and I think Fermat may have been in on it, and a few others. And they did a lot of early work. Not only they mentioned mathematics and physics and calculus, they did some of the early work with statistics. Okay? This, to me, if I'm remembering right, I may have them confused with someone else. Not that impressive was their work in statistics, because they basically developed a lot of this for the sole purpose of being able to gamble and, get your hands up and gambling with other people. Because they were pretty big gamblers from what my memory is. I may have them crossed up with someone else. It was waited until the time of about Florence Nightingale when she started applying statistics to something rather than games of chance. Okay, she used statistics in a very constructive and beneficial way. They were not particularly known for that, but that's beside the point. Okay, let's see how the book did the same problem. Because the weight density of water is 62.4 pounds per cubic foot, sheet is submerged in 6 feet of water. The fluid pressure on it would be the 62.4 times 6, which they got to 374.4, and it'll come back, I hope. Okay, good. Pounds per square foot, that's the pressure. And because the total area of the sheet is 12 square feet, and it's level at 6 feet depth, that means you just multiply those together and you get your 4,492.8 pounds, which is way more significant digits than you really have in this problem. Most you could get was 3, because 62.4 would be the most. Okay. The result, now this is what I was going to say, is independent of the size of the body of water. If this were in a swimming pool that was 6 feet deep, that would be the pressure. If that was in the Gulf of Mexico, saltwater. A freshwater lake, Smith Lake, at 6 feet deep, you'd be same pressure. As long as it's freshwater at 62.4 pounds per square foot, that would be, no matter where that body of water is, how big, how deep, how anything else, if you're 6 feet down, that would be it. Okay. Now, the definition of force exerted by a fluid. A force F is exerted by a fluid of constant weight density W. Constant weight density W per unit volume against a submerged vertical plane, vertical now, not horizontal, from y is equal to c, I think it's the top of the plane, to y is equal to d at the bottom of the plane, one way or the other. That would then be the weight density, which is a constant, it can come out, times, now here goes our limit. This is our partition here. The partition's going to 0, n's going to infinity, I is equal to 1 to n, of your depth. Now this depth is a function of your depth of water. You're going from c equal, y is equal to c, y is equal to d. The y of I is something in between those two values. Here is a function they throw in here, L as a function of that same depth, whatever depth you happen to be at any given y, okay? Times your delta of y. Well, what is this? This is your length function. The depth function is a function of depth, but also the length is. So if you have a strange shape here, and the shape is changing, the length of any strip is changing with the depth, that's the function that's describing that change. This is the depth of the water with it as y is changing, and then the thickness of that, because the thickness of a delta y is going to be all at the same depth. Okay? So this then translates to the integral of your weight density, which is constant. That's what we're saying, constant weight density W. Going from C to D, C would be the shallowest part, D would be the deepest part. The H of Y, that is your function of the depth of the water as a function of Y. The depth of your plane as a function of Y. Because we are talking about a plane, right? No. Yeah, a vertical plane, okay? The length function of that plane times your dy. So here is a length dimension, length dimension, length dimension. This is a cubic feet or cubic meters, and this is pounds per cubic feet or per cubic meter. That gives you your pounds or newtons. Where h of y is the depth of the fluid at the position y, L of y is the horizontal length of the region of y at y. Okay. Now, what they haven't said is where are you measuring your y from? Okay. What are you using as your y? And that's an issue. Okay. Here's a vertical gate in a dam that has the shape of an isosceles trapezoid. What do we mean by isosceles trapezoid? The two slant sides are equal, okay? Equal in length and probably also equal in their angular dimensions there. I think they have to be both of those equal. Isosceles trapezoid, 8 feet across at the top, 6 feet across at the bottom, with a height of 5 feet, okay? Shown in this figure. What is the fluid force on the gate when the top of the gate is 4 feet below the water level? Okay, surface of the water. All right. Now, the problem is figuring out those functions. Your h of y function, your L of y function, figuring out what in the world you're talking about the y being anyway. Okay. I hope you see the dy's are the only choice here, because that dy is all at the same pressure. Okay. So we're going dy's here. So let's put that in. So that thickness here is your dy. Okay? Now, the L of y we have to figure at some point. So the L is this length here. This is your L. Okay. Now, let's use the fact that this triangle right here, if you get right in the corner there, 5 is to 1, okay? Because this is 6 feet this way, you're a foot short here and a foot short there. So remember the isosceles, you're assuming the angles are the same, okay? Same length, same angles, okay? So, I think that's the only way it could be. If there's any different angle, it would be a different length, okay? So that almost guarantees it. So this triangle here is 5 is to 1 as L is to some sort of a length this way, okay? No, wait, that's not quite right. Let's do one on both sides, okay? So 5 is to 1, okay? That's going to be the ratio of, okay, the length is going to be at least 6, okay? And you're going to have these 2 increments added to it as you go, okay? And see, can we combine them together and make them make more sense that way? I'm not sure about that. Probably. Okay. So this triangle here is similar to this triangle here is similar to that triangle. This triangle is similar to that triangle, the big long triangle. Okay. That's what we're going to use to get our L as a function of depth. Okay. Now, the question is how to do the Y's. Okay. Let's see if they show the next picture. Yeah, here we go. Let's use their picture because theirs is a bit cleaner than mine. Okay. But that's the setup, and that's how we're going to go. Yes.
Why is it a 1 on the side?
Okay. Because you know this is 6 feet this way, this is 8 feet this way. These are similar triangles, so it's a 1 foot on the side. Right? So 6, 7, 8. Yeah. Okay. Yeah. I was just doing the triangle there, the right triangles. You could push them together and make it an isosceles triangle, but I think the right triangles would be easier to work with. But let's see how they proceed with it. Okay? So, in setting up a mathematical model for this problem, you're at liberty to locate the x and y axes in several different ways. That's why I said one of the choices you have, where in the world is your y-axis? How are you going to locate that? Okay? A convenient approach is to let the y-axis bisect the gate, go right down in the middle here, and place the x-axis on the surface of the water up here. Now, it would make sense to me to have y being positive down. But this book absolutely does not do that. So we won't. We'll keep it negative here. So we've got to flip things around to make sure they're going to come out okay. So if you choose their orientation here, the y bisecting the gate and x being the surface of the water, okay, then we know this point down here, since this was 8 feet this way, this is bisecting it, it's going to be 4 on the x-axis and minus 4 on the y-axis, since you're choosing y negative down, okay? Your base down here is going to be 3 on the x, because you came in 1 foot, and you went 5 more feet down, so this is minus 4, you go down to minus 9. Okay? The delta y is going to be the thickness here. That's the easy part. Now, what is your depth of the water, your h as a function of y? Well, since you've chosen y to be negative downward, you have to make that depth minus y. See, it would have made so much more sense to me to make y positive downward, and then this would be the depth would be y, and that would be a piece of cake. But since they oriented it this way, you have to have that be minus y. So that's a really easy function. That one's easy to get. Okay? Now, the L, that's going to be a little more. And they're representing that by the x here. This is going to be L over 2. Okay? Well, what would this be? Okay? And I guess the way they're going to approach it, just by the way they've set it up here, is come up with an equation for this line, and that would, if you have this line as y as a function of x, it's easy to change that as x as a function of y, and then go for it, okay? So rather than worrying with the triangles like I was suggesting that we do, they're just going to do it this way. So let's see what the equation for this line is. Obviously, it has a slope of up 5 for every 1 to the right, right? So that's going to be a slope of 5, right? Now, it's not too obvious. Okay, so that line is y is equal to 5x plus b. Okay, where b is going to be your y-intercept. Let's pick any one of those points, like 4 minus 4, and that would be minus 4 is equal to 5 times 4 plus b. So this would be minus 4 is equal to 20 plus b. b is equal to minus 24. Okay, now is that helpful? Y is equal to 5x minus 24. Okay, let's solve that for x. So y plus 24 is equal to 5x, and divide by 5, and you get x is equal to 1/5. Well, don't do it this way, okay? 1/5 y plus 24. Now, that was done fairly rapidly. Let's make sure it works. Okay? When y is equal to minus 4, this would be 1/5 of 20. X should be 4. Yes? And when y is equal to minus 9, this will be 15, and x will be 3. That looks like it works. So this is your x as a function of y. Well, your length is 2 times x, right? So let's make that 2/5. So your L of y is equal to 2/5 y plus 24. Okay? Here is your h of y. Okay, ooh, not very pretty. Okay, I think we got it now, don't we? Okay, let's see. This is water, okay? I wanted to make sure we were doing it with water. And everything's in feet, if my memory's right. Okay, I believe it is. So let me make sure I've got the right question. What is the fluid force? Yeah, okay. I want to make sure we were answering the right question. Okay, so F is equal to the weight density, 62.4. I'm going to leave off the units for now, times the integral. Now, our integration. Really doesn't matter how you do, but I think everything will come out better if we start at the bottom and go up. It seems a little bizarre. You're doing your dy's, so you're going from minus 9 to minus 4. This up here, you're not minus 9 to minus 4 because it's the fluid force against the gate. So from minus 9 to minus 4, okay, you got a minus y, so I'm going to put the minus on the outside and put the y, that's for the h, okay? And your L function was 2/5, so let's put that on the outside. I wish I had them all in decimals now, okay, I don't. 2/5 times y plus 24 times your dy. Okay, now unless I've done something stupid, I think that probably is going to take care of it. So let's get this constant out front into a decimal. This is 0.4 times 62.4. What is that going to be? I should be able to do that in my head, but I don't feel like it today. So
24.96.
negative 24.96. Is that what you said? Okay. We'll just do it that way. Okay. Now, let's see what we got. I think it would be beneficial. Minus 24.96. That's close enough to 25. I want to just write 25, but let's keep it from minus 9 to minus 4, and that'll be y squared plus 24y dy. Okay, see? The calculus is the easy part of the problem. Setting up the stinking problem, that's the hard part, okay? Because the calculus is pretty easy. What is the antiderivative of that? Y cubed over 3
Plus 2y squared over 2.
is that like 12y squared?
Oh, yeah. Sorry.
Okay,
I read
good.
it wrong.
Okay, 12y squared, and that's evaluated from minus 9 to minus 4. Okay, now, again today I don't feel like trying to do that in my head, so if someone will punch in the numbers. Ooh, boy, let's hold off this for now and just do minus 4 cubed, I think that's minus 64, divided by 3, plus 12 times 16, okay, minus and when you put that in there, boy, what's that? 729 or something like that. But it's minus and minuses plus that over 3, whatever that turns out being. I'll let you do it on the calculator. And then that will be a minus 12 times 81. Finally get that. Whatever that comes out being times the negative 24.96. That should make it go positive again. I hope. Anyone been able to punch in the numbers? Okay. What do you get? They leave out lots of steps in the book. Do you get anything close?
I had been doing it with the positive.
Oh, I see.
So I don't know if my number's going to be the same.
What number you get? Huh?
Negative 1,675 over 3. Putting it decimal.
Okay. They got something like 13, almost 14,000, so that sounds like we're sort of way off there. You get it? Okay. 13,936 or somewhere thereabouts. Yeah. Okay. That's what we got in the book. I may have said some numbers wrong or something when I was doing it in my head, but we did it the same way they did, and we should get the same answer. Okay. Now, keys here. How I was going to approach the problem was geometrically figuring the length of this. But when you set up a thing like this, that gave you a straight line that you can come up with the equation of the line. And I don't know if that's how the book did it. Yeah, they ultimately came out with the equation of the line. They did the slope. They calculated the slope and then did the, well, and we did too. Yeah, we did too. And then plugged in the points. They just used the other points, but it came out the same equation. So, but then you get it in terms of x because you're integrating with respect to y because you're dy, so you need this as a function of y. So even though that came out in x, solve it for x so you get it as a function of y. And those are the silly little things that you'll sometimes forget about when you're trying to do it, and then you try to set up your problem and say, wait a minute, I've got x's and y's in here, so keep that going. All right, any questions on that? Oh, let's see how they do it. Let me erase my scratch. I've been talking about how they were going to do it. Let's see how they did it. Okay, so the depth of the water at y in feet is h of y is equal to minus y. And that's why doing the integral, having the orientation like they say just makes it a little on the awkward side. To find the length of a region, find the equation of the line forming the right side of the gate. Okay? And that's why they did midpoint. That works really nicely. Because that line passing through points that and that has this, and we did it. Here's Ricky. If I can find my pen. There it is. Okay. Does anyone else come in since we called roll? And we've still got a segregated class, so that's good. Okay. Don't know why. Okay. There's the equation for the line, and this point slope equation. They just chose a different one than what we did, and that's what it came up. And they got y is equal to 5x minus 24, exactly like we did. But we want that in terms of x, so it's 1/5 of y plus 24. Okay. You can see that the length of the region is in twice that, so that would be 2/5 times y plus 24. That's your L as a function of y. Finally, by integrating that from minus 9 to minus 4, you can calculate the fluid force by that, leaving just expressions in there. If you plug in what we knew, W was 62.4, H of Y was minus Y, L of Y was 2/5 of that. Certainly I like the minus out and the fraction out. And they did that here, and that left them with y squared plus 24 dy. That would be y cubed over 3 plus 12 y squared. Perfect from those two. Skipping all the gory detail of how they got there, that's the number they came up with, and then multiplying those out gave them something in the order of 14,000 pounds. And by the way, you don't have 5 digits of precision here, so 14 would be generous. Certainly, this was only good to 3, but everything else is only good to 1, unless you have the decimal after it. So 14,000 would be actually generous in significant digits, and it's close enough for government work. Okay. Whoa. Now the bad news is they did not do example 3. Only 3 examples in this section. All right, so let's us do example 3. Were there any questions about it? I erased it, but I can bring those back. Anyone need those up longer? Okay. Let's do example 3. A circular observation window at a seawater aquarium has a radius of 1 foot. Okay, I guess I'm going to have to draw a picture of that. Okay, now they're going to put our axes right down the middle of that window. This is going to be near the bottom here. So let's just do a tick mark there, 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 and there. Ooh, too far out. I'll do terrible job of drawing a circular shape. So this is 1 foot radius. Okay? Okay, 1 foot radius. And the center of the window is 8 feet below the water level. Well, let's let this line be my water level. So the center of that window is at 8 feet below. Okay. Let's see. There's 1, 2, 3, 4, 5, 6, 7, 8. Okay, something like that. Not very evenly spaced. What is the fluid force on the window? Well, obviously, we're going to need little strips of delta Y. Now, we're going to need to come up with what the length function is here. Okay? Now, it's perfectly all right to double things across the y-axis in your calculation. Don't even try to double things across the x, because your pressure is getting greater as you go down. So don't try that. But it is going to be okay to double the length. So we can go 0 to r out there, and that would be okay, and we'll just double that. That's going to be all right. But we can't do the top half of this and then say, oh, we'll just double this and do the bottom. Don't even try that, because it won't work. Because we're increasing in, your H is increasing, even though L is not, the H is increasing with that. Okay. So, what we have to do is figure out what this X value is here, and then get that in terms of Y. Okay. It just happened to be, I drew this fairly close to being spot on there. This is 1 foot radius, so this is going to be something going from 0 to 1 as you go down, and then 1 to 0 as you go further down. So this is the X here. All right. This arc of that circle could be expressed as the square root if this is 1, this is x, the depth here is the square root of 1 minus x squared, x squared minus 1. No, 1 minus x squared, I can't. This is so tiny it's hard to write. Okay. If this is x, this is 1, then the y here is going to be y is equal to the square root of 1 minus x squared. That's your height above there, and that's where we put our axis, so that's going to be okay. This is this y right here. Okay. Now, squaring both sides, y squared is just completely reversible, is equal to 1 minus x squared. So x squared is equal to 1 minus y squared. So x is equal to the square root of 1 minus y squared, which I could have done that the other way. Oh, please tell me you're going to cut. Okay, there we go. Now, that is the length here, and of course 2x would be double that. Okay, so your length function 2 times the square root of 1 minus y squared. Okay. Sorry, this is flipping like this so badly. Now the problem comes I think that'll be okay, because even when we are doing from the -1 here, that will still work there up to a +1. So we're only integrating from -1 to +1. And that, I think, will take care of us here. Okay? So I think that's going to be okay from down here to up there. I believe that's going to be all right, this function here. Now your depth function, that is going to be your h as a function of y. Okay. Where y goes from -1 to 1, your depth there is going from y is, let's see, how the best way to say this. Try it this way. H is equal to 8 minus y. Is that right? Or plus y? I believe minus y will do it. Okay? So when y is -1, that would be 9. And when it's +1, that would be 7. So yeah, your depth will be, that fits. So there's your h function as a function of y. Okay. And this is just water, right? Oops! Messed it up. Well, I haven't messed it up, but I was thinking wrong. A seawater aquarium. Seawater, the density is 65, isn't it? No, 64. 64. Okay. Window at a seawater aquarium. Okay. What is the fluid force there? So the fluid force is going to be 64. They put a 0.0. We can live with that. Okay. Times the integral. And our y's are going from -1 to 1. dy out here. Your h function is 8 minus y. And your y function is the square root of 1 minus y squared. Now, oh, times 2. I left off that. Okay. Okay. I'll put the 2 out front with the 64. Okay. Now, what they do is break this up into 2 integrals. And 2 times 64 is 128. Okay. The first of these is going to be times 8 times the integral from -1 to 1 of square root of 1 minus y squared dy. Okay. That's going to be the 8 times that. I put the 8 on the outside. The second one of those is going to be plus our 128 times the integral from -1 to 1. Let's make that a minus 128 because of the minus sign there. Okay. times y on the square root of 1 minus y squared dy. Okay. Any suggestions here? I've got to erase some stuff somewhere. Well, maybe I can write up here. Let's try that. 8 times 128. Someone help me out there. I don't want to do that in my head. 1024. I should have known that. Okay. 1024 times the integral. Now, I don't want to do that as that to the square root. I want it minus 1 to 1 as 1 minus y squared to the 1/2 power. I don't think that's going to be helpful, but I just don't like square roots there. Well, actually, now I'm wishing I had left it in square root. Except we haven't done the technique necessary to do that. In the next chapter we do, we'll come into a technique to solve that very problem. We don't have that technique under our belt yet. So how does the book do it? I see. They just skirt the issue. Okay? They say that's a semicircle, right? And it is. And so the area of a semicircle is 1/2 power squared. Okay? So you can divide out a 2 again and just do power squared. And it's radius 1, so yeah, they wiggled out of this one. So this will be 512. My pen is ugly. 512. Okay. Times pi, right? 512 pi. And then, as I said here, what was the rationale there? Second integral, because the integrand is odd, limits are symmetric, it's going to be 0. We could have actually calculated that one, because this is a substitution that u equal 1 minus y squared du is equal to minus 2y. There's you could do that, but you go through all that and you wind up being 0 anyway. So it says the answer is 512 pi, and that's what they got in the book. So they wiggled out of doing that without any further ado. Okay. Homework exercise. That finishes 7-7. Homework exercise is either 3 or 5. They're both at Calc Chat. 3's at Calc View. 7's at Calc View. Any of the odds 9 through 13, they're all at Calc. No, I'm sorry. 7's at Calc Chat. Any of the odds 9 through 13, they're all at Calc Chat. 13's at Calc View. 15 or 17, both at Calc Chat. 15's at Calc View. 19 or 21, both at Calc Chat. 23's at Calc Chat. Either 25 or 27 if you want to. You don't have to do those, but if you find them interesting, they should be at Calc Chat. And then any of the odds 29 through 35. They should all be at Calc Chat. That finishes the chapter. If you need more exercises to do, I'm sure you feel like you do, odds 1 through 9 are at Calc Chat, also in the back of the book. 11 or 13's at Calc Chat, 15's at Calc Chat, 17's at Calc Chat, 19, 21, any of, either 23's at Calc Chat, 25's at Calc Chat, 27's at Calc Chat, 29, 31, and I'd say any of the odds 33 through 39, all at CalcChat. 41 at CalcChat. 43 is at CalcChat. 45 is at CalcChat. 47 is at CalcChat. And either 49 or 51 should both be at CalcChat. All right. Now, this isn't probably too bad a time for a break, is it? Okay. Let's try to keep it less than 5. I've got to run down, and hopefully she's run off the copies of the test for Chapter 7, and I'll get back up here. And when we get back up, we'll start Chapter 8. So let me go and get Chapter 8 set up here. (8.1), and I'll go down and see if she's got the test ready. All right, so I'm going to pause. Okay, we are recording again. Let's get that up from the current slide. And before we get there, let me say this about the test. I think I've said it before, but just in case you didn't hear it or people at home didn't hear it, I just passed out the first test covering Chapter 7. Okay, 10 questions, 2 pages. There's some room for work on this, and you got the front and back also that you can work on. But I do need to see your work. Okay, I think I told you this before. I've got some guff from some of the other instructors. Most of them don't teach the same course as I do. In fact, I'm the only one. Well, one other instructor, he doesn't give me any guff about the Cal 2, but in Calculus 1 and some of the other, well, that's about the only thing we have in common. They really gripe that I'm giving take-home tests. But the thing is, I don't think these tests you could finish in an hour. So either have to simplify the test or, so I like the idea of take-home tests. But the gripe is that the grades get inflated, and they have their ideas of the reason for that. So what sort of my compromise is, I need to see all your work. So you can't just get an answer somewhere and write it down. If you do, you won't get more than half credit for the thing. If it's a correct answer and I have no work, you'll only get half credit for that. So if you just give me 10 correct answers or however many blanks are on the page, the maximum score you can get is a 50. Okay? So please show me all your work. That way also, and I used to just do it the other way, say, if you show your work, I can give partial credit and try to encourage people to show it. Now I say you're required to show your work to get full credit. Okay? So any questions on that? Now you have at least a week to work on this. You have longer if you need it. But the reason I give you a week, 2 reasons. Number one, if after looking over it this weekend and you come in Monday and say, I don't understand really what you're looking for in number 7, or something like this, or, blah, blah, something like that, then, or I can't quite figure out what this symbol is, or something like this. It all looks pretty clear to me, but it may not to you. You can always ask questions, okay? The second reason is you have the weekend, okay? In case you need the weekend that you're working during the week, you always have a weekend. Now, like I said, I will give you more time if you need it, but I do not want this test out when I give you the test for Chapter 8, because I don't want to correct the same errors twice, okay? I want you to get this one in, and I can get it back to you before the next test. So try to get that done. Any questions on that? Now, another thing about asking questions on it, here's a question. I will answer the question, okay, but probably not to your satisfaction. Can you do number 4? My answer will be yes. Maybe that's as much as you get, okay. Now, how do you do number 4 if it's a conceptual thing, maybe a little? The far better question, can you do number 12 on the, 13 on the homework exercises? A question very similar to number 4 here. I'll be glad to do anything from the text, or from any text. So bring a problem from your mother text, or go to And that's why I keep saying it, calcchat.com or calcview.com, and see if you can find one similar to it there. Let's see how to do it. And if you can't, if you don't know how they got from this step to that step, that's a good thing to ask in class. Does that make sense? All right, good deal. Any other questions? All right. Chapter 8, integration techniques and improper integrals. We're going to focus on integration techniques, okay? I'm not even sure we'll do any improper integrals because it seems like if they're improper, we probably shouldn't do them, but we may just give them a parting shot, okay? 8.1, basic integration rules. I think you know most of these already, but let's hit it. Oh, the objective here, review procedures for fitting an integrand to one of the basic integration rules, okay? And the first subtopic is fitting integrands to basic integration rules. All right. Here are at least 20 of the basic integration rules, and you should know them all or be familiar with them. If you have an integral of a constant times some integrable function, pull the constant out and integrate the function. If you have the integral of the sum or difference of two integrable functions, that's the same as the sum or difference of the integral of those two integrable functions. Okay? Now, sometimes this is easier to do than that. Other times, this is easier to do than that. So do whichever is easiest. And, of course, this one, the antiderivative of du is u plus c. Indefinite integral plus c. Okay? A power function, whatever this is here, then that would be the antiderivative. If you use a constant here, okay, raised to power, you increase it by 1 and divide by that exponent, the new exponent, plus c. Now this works only when n is not minus 1. If n was minus 1, this doesn't work. What if n is minus 1? Then you use this one. Okay, the integral of du over u is log u. Now, technically correct, put them in absolute values there. If that's u is something that's always positive, you can leave off that absolute value. Okay? And my favorite of all time, the antiderivative of e to u du is e to du. I love that, like that. If it's any other exponential function, a to the u, then it's sort of related to that. It has a to the u in the answer, but then you divide by log a. Okay? ln a, by the way, not just log log. ln. Okay? Antiderivative of sine is minus cosine because of the switch, and antiderivative of cosine is sine. Of course, plus c. Antiderivative of tangent, I don't know if you remember that, is the minus the log of cosine u du, which quite often isn't expressed that way, but they're doing it here. You could also say, if you did this as log of this is minus 1, that'd be log of secant. Quite often you'll see it that way rather than minus log of cosine plus secant. Either way, same thing here. That would be antiderivative of secant u is log of secant u plus tangent u. One to use the tables for. I don't like to memorize things. That's it. Have to have absolute values because it's a log. And then, of course, with cosecant, you need the minus sign in front of it. Secant squared is just tangent because derivative of tangent is secant squared. Cosecant squared minus cotangent. Also the same thing. Secant tangent is secant, cosecant cotangent minus cosecant. Those we've had. Now, I guess in passing we had done these. Do y'all recall? Okay. They're given to you here. Later we'll have a technique for how to come up with those yourself. Okay? For right now, just go to the table and use it. Okay? One of the sections in here is going to be trigonometric functions. Trigonometric integrals, that's it, trigonometric integrals. Those are going to be done with that technique. Because this chapter is talking about the techniques. So those are the basic integration rules. So, it says find each integral, okay? Of the ones we just looked at, what is this closest to? Let me get my pen set up. This is most similar to, let's go back to this one right here, number 90. Something with your variable squared in there. Here the A is the constant and U is the variable. Okay? So you see that one is very similar to it. You have some fiddling around you have to do, but that's easy, fairly easy to fiddle. Okay? The next one, that's basically closest to, believe it or not, this one, okay? Because you see the du, if you let the u be the denominator here, the du is pretty close to the numerator. Not exact, but close, okay? And then this one, okay. What is the technique for that? Wait. That's right, wait. Y'all have done substitution, right? Yeah, this is a substitution problem, and it comes out leading to that. That's what I should have said here. That one is close to the one I said. This is a substitution problem. Okay. I forgot. I was thinking Cal 1 class. Cal 2, y'all have already done substitution. That's basically a substitution. Okay, this one, frankly, I think a substitution is also going to be the key to this one, but it's going to take a little bit different approach. Okay, but that's what I would try. Most complicated part of this is just the denominator, and let that be your u. And then, if u is equal to this, then x squared is equal to u minus 9. And then plug that in here. And I think you'll be able to work it out that way. Okay? Now, they say find the integral, so let's do it. Okay? And we're going to use substitution. Okay? So here, well, not substitute, use the table. This one's going to use the table. And this is similar to the form, and I'm going to write it, of this one right here, number 19. The integral of du over a squared plus u squared is equal to that. And we'll know how to do that in a minute, but let's write that one down. Oops, right, wrong way. The integral of du over a squared plus u squared is equal to 1 over a arctangent u over a plus c. 1 over a arctangent, I prefer inverse tangent, okay, of u over a plus c. Okay, now that's what we're going to go from. Okay, we want to get that to look like this. Actually, there's only one step we have to do. Bring the 4 on the outside. 4 times the integral of dx over x squared plus 9. Right? Now we're just like this. That would be 4 times 1 over a. Okay, what's your a in this problem? No, a squared is 9, so a would be 3. Okay? So that would be 1 over 3 times the inverse tangent of x over 3 plus c. Okay? So cleaning that up just a little bit, 4/3 inverse tangent of x over 3 plus c. Okay? Now, again, our techniques we're going to get to in a couple of sections, 2 or 3 sections, 3 or 4 sections, we're going to get how they got that. Right now, using that table, you got it. Okay? Now, the B one here. I sort of gave you a hint. Let me use the space underneath it here. Okay? What's your substitution? What would you use? X squared plus 9. Perfect. And then what's your next line usually after that? Then du is equal to 2x dx. Okay? We've got a 4x dx, don't we? We don't have a 2x. So let's multiply that by 2 and multiply that by 2. Now we got a 4x, don't we? Okay? So what do we have now? The integral. And we'll have a 2 on the outside. This 2 goes on the outside. Okay? Of du. 2 du was this 4x dx. So the 2's on the outside over u. And what is that? Second? ln of u. And what is u? What are you? No, okay. X squared plus 9 plus c. Now, I can hear someone screaming in the background saying, you didn't put absolute value bars over that, did you? Do I need them? Why not?
Always positive.
Always positive. Squares are always positive. Add 9 to it, it's going to be even more positive. Worried about here. No, you're worried about 0. It can't be 0 either because you're adding 9 to it. All right, so there's that. Not too bad, was it? Now this is the other one that a little bizarre. Okay. Let, what was my suggestion? U equal, anybody? X squared plus 9. The most complicated looking part of it, certainly the denominators are usually more complicated than what? Du is equal to 2x dx. Now, this may not work. We'll see if it does. Okay? Because we needed x in that numerator that we don't have. But let's take this and expand that. Okay? To x squared is equal to u minus 9. Okay? Now that's how I was starting to handle it, but I'm not sure this is going to work now anymore because of the x dx in there. What you might also extend that to be x is equal to the square root of u minus 9. Now that should be a plus or minus, and maybe we need that. We'll come back to that in a minute and see if that helps. Don't know if it will or not. All right. So what do we have now? This becomes the integral. And again, I think we need to multiply by 2. So we have a 2 the 4x squared dx is going to be before I carry us down the wrong rabbit trail there. Wrong. Obvious thing, and I blew it. And y'all didn't catch it. What's wrong with you? Cardinal rule when you're doing rational expressions, if you have an improper rational expression, divide first. Got it. So that's our technique. Let's first divide. Okay? Let's do that up here. X squared plus 9 into 4x squared. Okay, I think we can do it just like that. Divide. What do you get? X squared into x squared? 4 times, right? Multiply. 4 times x squared is 4x squared, and 4 times 9 is plus 36. Subtract, and you get, this is a 0 up here, and change signs and add, subtract, whatever you want to tell it. That's a minus 36, right? So what this becomes is the integral of 4 dx minus the integral of 36, and we could have put the 4 on the outside, I should have, the integral of 36 times 1 over x squared plus 9 dx. Okay? You see what I did there? If you write this result up here, let me clean this up just a little bit. Okay, ooh, that's ugly. Okay. This would then be 4 plus, whoa, wrong. Okay, 4 minus 36 over x squared plus 9. You see? This divided into that goes 4 times with minus 36 left over, so you write the remainder over your division, right? So I've integrated 4 dx, then minus 36 that. So this is what this becomes. And the first part is pretty easy. What's that? First integral. 4x, okay? Minus 36 times, oh, have we seen anything like that before? Yep, that was number 19 again, wasn't it? In fact, it was exactly 19 again. The A up here, once you pulled the 4 out, that was minus 36 times 1/3 the inverse tangent of x over 3 plus c. And then this 36 will go into this is 12. So that's what I think our answer is. 4x minus 12 times the inverse tangent of x over 3 plus c. Yeah. Okay. All right. Sorry about that, leading us down the wrong path. Okay. 1a, the arctangent rule, which I didn't know we had an arctangent rule, but here it is. U equal 3, U equal x, a is equal to 3. That's from the number 19 from before. This becomes 4 times that, and that would be 4 times 1/3 the arctangent of x over 3 plus c, which is 4/3 arctangent of x over 3 plus c. Do y'all remember an arctangent rule? I don't, but I mean, I know it's true, but I didn't know we had covered that. Maybe we did and I forgot it. Okay. The B part does not apply here because the numerator contains a factor of x, so you just do a substitution. Okay. And that's exactly what we got. They didn't show how you got it, but it is exactly what we got. And that's 2 times du over u, which is 2 log u, which is 2 times, and because the u is never negative, x squared plus 9 is never negative, you can put it in parentheses. Okay? Just like we got. Okay? And then the third one, because the degree of the numerator is equal to the degree of the denominator, use first division to rewrite the improper rational expression function as a sum of a polynomial and the proper rational expression. Polynomial is just going to be 4, and then your remainder over your divisor, and then that becomes 2 integrals, both of which are not too bad. The first one's just 4x, the next one is just minus 36 times the same problem, 1/3 arctangent x over 3, which is 4x minus 12 arctangent plus c. Because these are indefinite integrals, always use the plus c. Okay. Any questions on those? All right. More, let's see. Wow, we got a bunch more examples before we get to those. So let's back off. Okay. And try to do, how are we doing on time? Oh, we got plenty. Example 2. Evaluate this one. This is not an improper integral. This is a definite integral. 0 to 1, x plus 3 over the square root of 4 minus x squared dx. Believe it or not, they showed us the easy ones. This isn't bad, but you just have to know where to go with it. What in the world would you do with that?
Do substitution.
Second?
Substitution.
Okay. Actually, substitution may not be a terrible idea, but what did someone say? Split it. Let's do that first and then substitute. Okay? All right. So what do you mean by splitting it? Okay, a little louder. X over the square root of 4 minus x squared dx plus 3 times the integral 0 to 1 of dx over the square root of 4 minus x squared. Is that what you meant? Is that what you were saying? Okay, I just don't hear well. Okay? My wife says I don't listen well either, but that's beside the point. Okay. Now, it's your turn. First integral. What was your suggestion? Substitution. Excellent. Okay. So what we have here then is let. What would be your substitution? We love u, don't we? In fact, who was it that called it a u substitution? No, okay, that was you. Okay. U substitution. So u substitute. Okay. What would that be? 4 minus x squared. Then what? Then du is equal to minus 2x dx. Is that what you got? Okay. Minus 2x dx. We don't have a minus 2x dx. We have a x dx, so let's divide this by minus 2, which will be dividing this by multiplying by minus 1/2. Okay? These go out. Okay? Now, it'll come back. What do we have now? We have an integral. Oh, good, surprise. But we have a change of, okay, we're going to have a minus 1/2 out front. Okay? But because we have a change of variables, we also need to change our limits. So when x is 0, what is your u? Not that hard. 4. When x is 1, what is u? What are you? Huh? 3. Okay. And your integral will then be, I pulled the minus 1/2 out front, and our x dx is u, or this is the du now, and down here we have a u to the 1/2 power, don't we? It's the square root of u, okay? Now, what's messy about that? 1/2 is messy, but it's not that messy. What's messy about it is you have your limits reversed. Can you flip these? Yes, you can if you do one thing. Change the sign. That reverses it. Okay? So now we lose the minus sign. So that gives us 1/2, the integral from 3 to 4, of u to the minus 1/2 du. I rewrote that, didn't I? That's a lot easier to integrate than something in the denominator. How would that integrate? Or anti-derive? 1/2 is out front. U to the what? Isn't it? You're taking a derivative, aren't you? It's antiderivative. You add one. Remember? Yeah, that becomes u to the 1/2, but then you have to multiply by 2, don't you? Divide by 1/2. Okay, go back to. That is the sound effects. Whoops, too far. It's right here. We have u to the minus 1/2. To minus 1/2, you add a 1, which makes it positive 1/2, and then you divide by the 1/2, which is multiplied by 2. Right? Okay. There we go. Well, multiplying by 2 wipes out the 1/2. You didn't like it before, it's gone, okay? Hang on there. Don't like the weather, it'll change, okay? And that's it, isn't it? Evaluated from 3 to 4. So let's actually do that while we're here. What's the square root of 4? 2 minus the square root of 3. That's the first integral, right? Yay or nay? You act like you don't believe it.
I believe you.
Huh?
I believe you.
Okay, I'm at Cameron.
I was just trying to find out what you were subtracting, but I got it.
Okay, you got it? Okay. All right. Now, let's do the second integral. Ooh, what does that sort of look like? No, it looks a little like it, but it has a square root and it has a minus. So let's go back to our table real quickly. Whoops, I overshot it again. That looks more like this one, number 18, doesn't it? Okay? For A is, I don't know what, we'll figure that out in a minute, okay? That's going to be arc sine, inverse sine of u over A, once we figure out what the A is. Okay. What you reckon A is? 2, exactly. So this will be, this one, let's do it like this. 3 times the, I believe it's just strictly an arc sine. I like to write it as inverse sine of x over 2, evaluated from 0 to 1. Okay? Now, this is 3. What's the inverse sine of 1/2? 30 degrees, or in radians, that would be pi over what? Pi 6, exactly. So this would be 3 times pi 6 minus the inverse sine of 0. Zero. Okay. So this part will just give you pi half, right? And that's a plus sign. Talk about a good irrational answer. What do we have here? 2 minus the square root of 3 plus pi halves. Okay. I sure hope that's right, all that work. Let's see what we got. Whoa, where are we? Example 2. Goodness, why can't they write an answer reasonably? They have a minus root 3 plus pi halves plus 2. Yeah, same answer. And then they plug it all in. Now, they obviously did theirs slightly differently from what I did. Now, it looks like they did it similarly. Yeah, but anyway, I don't see why they rearranged their answer that way, but they did. Oh, I see what they were doing. Yeah. No, I don't. Oh, they didn't use substitution. They didn't turn it around. So, yeah, it worked out the same. All right. Now, they also drew a graph with that one, and it came out looking somewhat trapezoidal-ish or something like that, and then doing an approximate midpoint solution, they gave, whoa. Oh, I'm sorry. They did numerically and did n equal 5 and stuff and came out with 1.837 rather than 1.839, which is mighty good. And they say, though, don't do it if you're near a vertical asymptote, which is always a good idea. So I don't know why they put that in there. Let's go on down to example 3. That was bad enough. Any questions on that before we leave it? Okay. Example 3. Find the integral of, this is an indefinite integral here, x squared over square root of 16 minus x to the 6. Such fun ones here. Okay? Which way would you head on this one?
I would probably do substitution.
Okay, and what would you substitute?
16 minus x to the 6.
Okay. Now, when you do a du for that, so I understood it to say is 16 minus x to the 6. When you do a du, you're going to get a minus 6x to the 5th, which is not going to be particularly helpful here. That's a 2, by the way. It looks sort of like a 3, but my pen drags if I don't pick it up soon enough. That's x squared. So this is a little bit stranger of a problem. Since you have an x squared up there, I think where they'd take us is trying this. let's write this as the integral of x squared, we'll put the dx up there in a minute, over the square root of 16 minus x squared cubed dx. Now, no, they actually do x cubed squared. I was debating, but let's do it that way. I think that does work out better. X cubed squared. Oops. Yuck, I can't write. No. All right. All right. Try it one more time. Squared. All right. Now, part of the reason for doing that is to do a u substitution with this. Okay? And when you do that, if u is equal to x cubed, then du is 3x squared. So now that fits better this way. And then you have a form, the du in the numerator, with some constants and stuff. And you have a 16 minus u squared down here, square root, which is one of those inverse signs. Remember? So I think that's the way to go. Boy, are they ever taking us down the rosy path here. Okay? Let's see if we can get that to work. Now this time we won't do the whole denominator. We'll just do let u equal x cubed. The innermost part of the most complicated part of the problem. Well, that's complicated, but here's the innermost part of the most complicated part of the problem right there. So then, what's our question? Next step. du is equal to 3x squared dx. Well, we have an x squared dx up there, so we need to divide by 3. Okay. So now we're okay in the numerator. I think this was indefinite, wasn't it? Okay, so let's see what we've got. This will equal the integral of du, that's the x squared dx. We need the 1/3 out front for the du, okay? That's your x squared dx is 1/3 du, there's what, okay? Over the square root of 16 minus u squared. All right. Now, remember what that one was again? Arc sine of what? Of what? U over A, and what's your A in this case? 4. Got it. Plus C. Okay? But we need to substitute back, and this will be a 1/3 the arc sine of x cubed over 4 plus C. All right. I think that's what we got. Let's see what they have. 1/3 inverse sine of x cubed over 4 plus C. Got it. Now they have a little gray blurb on the right inside margin on page 517, comparison of 3 similar integrals. Okay, let's do this real quickly. It's just a little bit of review. Okay, any questions on this one? I'll go and erase this because I don't have a lot of room here. Okay, all right. The integral of 3 over the square root of 1 minus x squared dx. What would that be? That's an X. It's ugly X, but it's an X.
That's another arc sign.
Inverse sine, exactly. Just pull the 3 out front, and then you got almost a classic setup. Okay, that's the arc sine. This looks very similar. 3x times over the square root of 1 minus x squared dx. What would you do with that one? Substitution. Let the substitution be your innermost part here, 1 minus x squared. du would be a minus 2x dx. So pull out a 3 over a minus 3 halves out here. Yeah, that's the substitution one. Okay, and then the last one here is the integral of 3x squared over the square root of 1 minus x squared dx. Now that's a real pill. Okay, if this was a polynomial down here, you divide. It's a radical down there. Yuck. Okay, so what in the world do we do here? Okay, that doesn't fit anything that we've done before. This exploration said, for any that can be found, do so. For any that cannot, explain why not. You just don't have anything you can manipulate here to get it. If you let a u substitution here go into play here, you need a x dx up here, you only got an x. So you have x squared, that's not good. Okay? You can't divide this into that because that's irrational, that's a radical form. So there's really nothing you can do with this that I can think of right now. So leave that one alone. Okay? Nothing so far. Maybe later, not yet. Okay. Now we got some disguise going on here. This is example 4. Okay? Find this, the integral of 1 over 1 plus e to the x dx. What in the world are you going to do with this?
Do substitution.
Okay, and what would be your substitution?
1 plus e here.
Let u equal 1 plus e to the x. Good try. What would that give us then? du is equal to e to the x dx. Okay? We don't have an e to the x up there with the dx. Okay? So this might be a little bit of a problem. Okay? Now, here's, okay, a trick. I can remember when my calculus instructor, I was on the quarter system. We had 5 quarters of calculus and 1 quarter of differential equation. And I was so fortunate. He was a professor, my calculus professor. I had the same one for all 5 quarters of calculus, which was really, really nice to have, except he was really, really hard. But he really taught it well, okay? And we finished the 5 quarters of calculus with about a week to spare, and this is a 5-day class week. It was a 5-hour course on a quarter system, and we met, I think it was 55-minute hours, you know, so, and we finished about a week early, so we had 5 days of class. He said, well, let me get you ready for differential equations. He knew we'd be scattered around to all sorts of different instructors, professors for that. So he said, let me get you ready. And he said, basically differential equations, what you do when you're trying to solve these, you try a trick. If the trick works, you call it a method. Well, that's what we're going to do here. I'm going to show you a trick, and if it works and you can use it, call it a method. Okay? Now here's the trick. We're going to take this numerator, because it looks maybe a little like the denominator, we're going to do something to it. We're going to add an e to the x here. Now that changed the whole problem, didn't it? Unless you subtract an e to the x here. Now it's the same problem, isn't it? But we can now split this into two integrals. This will be, and what didn't you say, split them up? Isn't that the term you use for it? 1 plus e to the x over 1 plus e to the x dx minus the integral of e to the x over 1 plus e to the x dx. Legal in most states? Okay. And what's that first one? 1. And what's the antiderivative of 1 dx? X, just x, minus. Now what do we do with that one? You're following the right rabbit hole before. What were you saying? Let u equal e to the x, then, or 1 plus e to the x, then du is equal to e to the x dx. Oh yes, this will be minus the integral of du over u, right? I know my writing is really ugly. Okay. Won't that be it? So you have du, e to the x dx is du, and this is u. Du over u, and what in the world would that be? ln of u. Okay? And you're going to have a plus c here, but we'll worry about that later. This is equal to x minus, plugging back in, the log of 1 plus e to the x. Now what's nice about that? That's always positive. E to the x is always positive, so 1 plus e to the x is always positive. So you don't need your absolute value bars. Okay? Now, is there anything else you can do with that? I think not. If that was a multiplication in here, you could make that the sum of two logs. If that's division, that's the product of two logs. That's an addition. There aren't any rules. Nothing you can do with that. So that is, I think, our final form. Now let's see what they, for some reason that's just flashing. X minus log of 1 plus e to the x plus c. Got it. All right. Do we have time for one more? I kind of doubt it, don't you? I feel really rotten because I got started late because I was trying to get the copies of the test done. I got a break in the middle and got stopped in the classroom by another instructor, and now we're in early, so it's not been a good day time-wise, has it? Y'all probably will never forgive me, okay? Write me up. Okay. Homework exercises in this section will include, we came close to finishing. Any of the odds 5 through 13, they're all at Calc Chat. 7's at Calc View. Any of the odds 15 through 45. Let's see. No, let's just start with 5 through 13. I think the rest of those are going to require some of the things we're going to do next. Okay? You can try some of them if you want to. We'll see. And then we'll get into some real techniques. This is just fiddling around with manipulating things, which is good, okay, and necessary. All right. You got your tests. Remember, I'm not going to be on campus at all tomorrow, so don't even come looking for me or calling or anything else. I may have some opportunity to check email, but with my eyes being messed up, I may not even have a chance for that. Because what I'm left with, my right eye is distance. I will have a hard time reading anything up close with it. This one is going to be bandaged all day. When it comes out, it will be close up. So I'll be better off then, but I don't know when the bandage comes off. Good deal. Take care. Have a good weekend. Working calculus will make it a good weekend, won't it? Good deal.